Hi everyone. In this topic, we're going to talk about balancing chemical equations and biofuels. We've already talked about measurements, so this is balancing chemical equations. All right, so we're going to talk about a typical thing that we use in chemistry, which is balancing chemical equations. And then in the second half of this topic, we're going to go over something a little bit more fun and talk about the chemistry of biofuels. So let's talk about combustion energy, because that relates to fuel sources. So combustion is the process of chemical burning, where you mix two things together, you light them on fire, and this causes a chemical reaction to take place. So in order to have a chemical reaction, we have two reactants that mix together, and they create two new products. So my question to you is, what do fires require to stay lit? Think about it. What kind of thing does it need in order to keep burning? In order to do this, fires need oxygen. If you smother a fire and you remove its oxygen source, it will die. So that's one of the chemicals that participates in this reaction. The next one is the fuel source, so like the log that you're burning. And we want to think about, what do they produce? So one of those things is heat. It's making heat energy that comes off. But the next thing that it produces is carbon dioxide. And the other one is water vapor. So CO2 gas, or sorry, H2O gas and CO2 gas. So this is the chemical equation for general combustion here. We're seeing some kind of usually carbon fuel source, carbon-based fuel source mixed with oxygen, and when it's lit on fire, it produces carbon dioxide and water vapor. Let's take a look at balancing chemical equations. We're going to be doing this with combustion equations a lot, and we're also going to be using it with all kinds of other equations in this class. So this is a balanced chemical equation here. You can see that we have what we call reactants on this side, reactants. Please make note of that. The things on the left side of your chemical equation are reactants. The things on the right side are your products. And you can see that there are numbers in front of each of these molecules. There's a 3 in front of the sulfuric acid over here, and there's a 3 in front of the water over here. These other ones don't have numbers. This is a balanced chemical equation because the amounts of atoms on one side of the equation are equal to the amounts of atoms on the other side of the equation. So these numbers here, this is a 1 that's implied, so we don't write ones down. So these are implied ones. These indicate proportions of the reactants and products that are present in the chemical reaction. And this is the ratio of these molecules to each other during the reaction. So what we want to do here is we want to look at how many of each thing are on each side. So if we look here, there's 2 irons on each side of the chemical equation. So these are equivalent to each other. If we look here, there's 3 oxygens. Actually, we're going to come back to oxygen. Let's undo that. Let's see here if I can do that. We're going to come back to oxygen because that one's a tricky one. Okay. Hydrogens, let's look at hydrogen. There's 2 hydrogens here, 2 hydrogens here. So they're equivalent. Sulfates, or sorry, 6 hydrogens. Sulfates, we've got 3 here. If we notice that number applies to the sulfate, we've got 3 here. So those are balanced as well. And oxygens, you'll find those are also balanced. We have 3 here, and we've got 3 here. We're going to go through this in more detail, okay? So let's take a look here. In order to understand why this happens, we need to look at the law of conservation of mass. So this was proposed by Antoine Lavoisier, and he said that nothing is lost, nothing is created, but everything is transformed. So what this means is that matter can neither be created nor destroyed, but turned into something new. And so that brings us to our law of conservation of mass, which is the sum of the masses of the reactants in a chemical equation is equal to the sum of the masses of the products, meaning that the amount of atoms on one side is equivalent to the amount of atoms on the other side of that chemical element. So let's work through an easier example here together. So balanced chemical equations follow the law of conservation of mass. What is on one side of the equation must be on the other side of the equation, or it's not balanced. Something has been created or it's disappeared. We can't destroy mass, we can't create mass, but we can conserve mass, take it from one thing and turn it into another. So let's take a look here at this example problem. So what I like to do is I like to identify each element on each side and just verify that they're balanced on each side, and if not, add coefficients in order to do so. So this is methane plus our ammonia. It's methane gas plus ammonia gas, and it creates our hydrogen cyanide. Cyanide is a polyatomic ion, which is why you might not have heard of it before. And this is hydrogen gas. So if we look, we have one carbon on this side, we have one carbon on this side. So carbon was not created or destroyed. Nitrogen, we've got one on this side and one on this side. Nitrogen was not created or destroyed. Let's take a look at our hydrogens now. Hydrogen has 4 on this side and 3 on this side, so we've got 7 hydrogens. Whereas on the other side of the equation, we've got 1 and 2 for a total of 3 hydrogens. So this equation is not balanced. We are effectively losing mass here because we've lost hydrogens. They've gone somewhere. So what we can do in order to balance this equation is to make sure that there's 7 hydrogens on this side and there's 7 hydrogens on this side. We need that to happen. And so we can put in coefficients in order to show that more of these things are made on this side. So what we can do here is we can actually put a 3 right in front of this hydrogen, which is going to mean that we have 3 of our hydrogen molecules, 3 of these things. Thus, we have 2, 4, 6 hydrogens plus this one here gives us 7 total. So now this chemical equation is balanced because we have 7 hydrogens on both sides of the chemical equation. So that's how you essentially balance chemical equations, is you check what's on one side and compare it to the other and increase the coefficients in front of the molecule. In front of the molecule, not these. These don't change, okay? We're going to talk about that in a minute. But the numbers in front of the molecule can be changed. Okay. All right. Yeah, so this is what I showed you here. We have one of these molecules, and 3 of our hydrogens. So H, H, H. These little numbers here, these indicate what is inside of the molecule, and we cannot change the identity of the molecule. So inside of this ammonia, there's a nitrogen, a hydrogen, and a hydrogen. If you were to change that, say you had NH4 instead of NH3, and you tried to increase the amount of hydrogens that way, you suddenly have a new molecule. You've created something new that was not involved in the reaction. So that's why we can't change those numbers. But if you change this number in front here, say you make that a 2, you're just saying that you have 2 of these now. So if I had put a 2 here, that's what this means. We've got 1, 2 of these molecules. But if you put a 4 here, then you're changing the identity of the entire molecule, which we cannot do when we're balancing chemical equations. So that's why that can't happen there. Okay, so in summary, kind of here's how you balance chemical equations. You write out the reactants and products, and you check how balanced each side is by counting atoms on each side, and then you balance the element that is not balanced. You might see it appears in only one reactant and one product. Those are going to be the easiest ones to balance. So what I mean by that is combustion reactions. C2H. Here's an example. Let me undo this, hold on. Okay, here's an example of a combustion reaction. It's going to go to CO2 plus H2O. So starting specifically with combustion reactions, these are notoriously difficult to balance. You want to balance everything but the oxygen first. Oxygen you save for last. Because if you look here, we've got an oxygen, an oxygen, an oxygen, and an oxygen. It's in all of the reactants and products, and that's going to make it kind of hard to work with. So we're going to start with carbon first because it only appears in 2 molecules. That's a lot easier for us to deal with. Same with hydrogen. It's only 2 molecules. We can deal with that a lot easier. Oxygen is usually going to give you some trouble on these. So you'll save that to last, and that'll make your life a lot easier. And I'm going to show you a method to balance combustion reactions that's going to be a little bit easier to understand because some of these problems can be harder than others, and combustion reactions tend to. So once you balance the element that only appears in one reactant and product first, like your carbon or hydrogen here, as opposed to your oxygen, then you can move to your oxygen, choose coefficients to balance other elements as needed. So then you can add stuff where you need it for oxygen. So it's kind of like guess and check. You guess, check, see if you're right. If you're not right, you can go back and revise it anytime. All right, so give this a try yourself. See if you can put coefficients here in front of the iron and the oxygen and the iron oxide that's produced in order to balance this chemical equation. So let's take a look at how to solve this problem. So on this side of the chemical equation, we have 2 irons and we have 3 oxygens. On this side, we have 1 iron and 2 oxygens. So I'm going to go ahead and start with iron first. So we've got a 2 here, so I'm just going to write a 2 down here. So our iron is now balanced. Let's take a look at our oxygen. Oxygen, we've got a 2 on this side and a 3 on this side. The only way to make those equivalent is to make that a 6, because 2 times 3 equals 6. And 3 times 2 equals 6. So what we need to do here is we're going to have to add coefficients in order to make this work. So we can add a 3 here and a 2 here, and that's going to balance our oxygens. Now if you noticed when you added the 2 on the other side of the equation, goodness. Okay, so when we added the 2 to the other side of the equation, that now makes our irons be out of balance. Because now we have 2 of iron 2. So we've got Fe2O3, and we've got 2 of these now. We've doubled that, which means that if we counted, we have 4 total irons on this side, and we've got 2 irons on this side. So we're going to up the number on the left in order for it to equal the number on the right. So we're going to amend what we wrote down, and this will now become a 4. So we've got 4 irons in our reactants, 3 O2 molecules in our reactants, and that creates 2 iron 2 oxides here in our products. And if we check, we've got 4 irons here, 4 irons here, 6 oxygens here, and 2 times 3, 6 oxygens here. So this is our final balanced chemical equation because everything on each side is equivalent. Let's take a look at how to balance chemical combustion reactions because these can be relatively challenging because, as I said earlier, we have oxygens in more than one molecule. So the trick to these is, number 1, leave your oxygens for last. Anytime you see an element that is in 1, 2, 3 molecules, you're going to need to wait on it. It's going to make your life more difficult if you try to start with it. So we're going to do that last. And then the next thing is using fractions to solve. And I'm going to show you this fraction method, which will help a lot. So let's balance everything first before our oxygens. So carbon, there's 6 carbons. We've got 1 carbon on this side, so we're going to fix that. So C6H14. Sorry, we're just going to add a 6 here. That way I don't have to write all that out. Now let's take a look at the hydrogens. We've got 14 hydrogens on this side. We've got 2 on this side. So something times 2 equals 14. That would be 7. So if we have 7 of those, that's going to give us 14 hydrogens total. Now let's take a look at our oxygens. Since we've saved those for last, right? We've got 2 oxygens on this side, and we've got 2 times 6 on this side. So we've got 12 oxygens here, and then we've got 7 on this side. So if we add those together, we're going to end up with 19 oxygens on this side and 2 oxygens on this side. So this is 19 oxygens on this side, and we've got still 2 oxygens on this side. So 19 and 2, there's not really a good common denominator for these. So what we're going to do instead is we're going to say that, well, we've got 2 oxygens on this side, and we know that in order to get it to 19, well, 19 over 2, if you multiply that by 2, this is going to give you 19, that fraction there. So we're going to put our fraction into our equation here. So what we can do is we can say that we have this plus 19 over 2 oxygens goes to 6 CO2s plus 7 H2O. All right, now this is not a whole number. We need to make it a whole number. So we can make it a whole number by multiplying everything by 2. So if we multiply everything by 2, the 19 goes away, and it's now a whole number. So we'll do that. 2C6H14 plus 19O2 goes to 2 times 6 is 12 carbon dioxides. 2 times 7 is 14 H2Os. Now let's check and make sure we did our work properly here. We're going to check our carbons, hydrogens, and oxygens on both sides to make sure they balance out. So our carbons, we've got 2 times 6 on this side. We've got 12 on this side, so 12 on both sides. Our hydrogens, we've got 2 times 14 on this side, so that's 28 hydrogens on this side. And we've got 2 times 14 on this side, so that's 28 hydrogens on this side. So far it's looking pretty good. Now let's check our oxygens. This is the true test. So we've got 19 times 2 on this side. It's 38. So that's 38 oxygens. Let's check our other side. We've got 2 times 12. So that's 24 oxygens plus this 14 here, plus 14. And that's going to give us 38 oxygens. So it worked. Our trick worked. So you can use this fraction method here in order to get yourself to these numbers, because if you guess and check, you're going to likely be going back and forth a lot. These are really high numbers, 19, 12, 14. Normally these are a lot lower, down to like 2, 3. At most you might see 4 or 5 as coefficients before molecules, but these combustion reactions can get really big. So more practice with this will help you. Okay, now go ahead and give this a shot yourself by seeing if you can balance this chemical equation using the fraction method that I showed you. So remember to balance everything but the oxygens first, since they appear in 3 of our chemical compounds. That's going to help you out a lot. And then balance your oxygens using that fraction method. Okay, let's take a look at how to solve this problem. So first things first, we'll look at our carbons. So we've got 4 carbons on one side, 1 carbon on the other. So if we put a 4 here, that's going to fix that issue. Let's check out our hydrogens. Hydrogen on this side we've got 10, on this side we've got 2. So 2 times 5 is 10. So if we put a 5 in the front, that means we've got 10 total hydrogens now. Let's take a look at our oxygens. So on this side, we have 2 oxygens. Here we have 8 oxygens because we've got 4 times 2. Here we've got 5 oxygens. So if we add that up, we've got 13 oxygens on this side and 2 oxygens on this side. Not very balanced. So we're going to use our fraction method in order to fix this. So we're going to do a 13 over 2 right here. So 13 over 2 times 2 is 13. Okay, that's why we can do this. So now what we want to do is we want to take that 13 over 2 and make it a whole number. And we can do that by multiplying it by 2. And when we do that, we need to multiply the entire equation by 2. So we'll just go right here, multiply everything by 2. And what we end up with is 2C4H10, 13O2. This is why that's a 13. Goes to 2 times 4 is 8 CO2 plus 2 times 10, 2 times 5, which is 10 H2O. So this would be your balanced chemical equation that you should arrive at for this combustion equation.